While we're dealing with numerical integration, the really important part when it comes to the way that we use these in engineering is that, yes, we're able to find an approximation, but that's useless unless we know how good the approximation is. So what we learn about is the concept of the error term. And the error term is simply how far are we from the actual value of the question. And what we learn are the various formulae for what it is. So let's stick with the midpoint error. That one is less than or equal to k times b minus a divided by 24 times delta x squared. I'm not a big fan of this formulation. This is what the textbook uses. I prefer to take this delta x, which is equal to just b minus a divided by n. Write it using that. So you have b minus a, one time over here, two times over here is cubed over 24n squared. That gives you a much better sense of what's going on. So k is the largest possible value for the second derivative of our function. It's going to be a constant. B minus a is a constant, 24 is a constant, n is the thing that you're changing. And you see immediately what's going to happen. If I double the value of n, it's going to cut the potential error by a factor of 4, and so on. It's quite useful. Another really nice thing that happens is that the error for the midpoint estimate is generally of the opposite sign from the error for the trapezoidal estimate. This over here, what it really gives me is the biggest possible value for the absolute error. But if you look at the error with the plus minus sign, if we take, let's say, a function that's concave up, right? So if we have a function that opens up this way, and we try to estimate it over, say, 3 segments. If you take the midpoint, so the midpoint is here, you've got that, you've got this, and you've got this. Notice what happens when we take the midpoint, then what we're going to have is that there is a small segment that is under the graph that we are missing, and there is another small segment that is above the graph that we count even though we shouldn't. Because of the concavity, because the function opens upwards, what has to happen is that this bit over here needs to be bigger than that one over there. And so what is the total is that we're going to have an estimate which is a little bit below the value of the actual area under the graph. On the other hand, if we decided to find this using the trapezoidal method, then when we connect these lines over here, because the function is concave up, what we're going to get is that these lines all lie above the graph. And so we are overestimating the value. And so what we get is that the error term in the midpoint estimate versus the trapezoidal estimate, they're related. You have that one is about twice as large as the other, but they also have opposite signs. And that's part of what leads to the idea of Simpson's approximation. The fact that you can look at these two things and say, well, you know what, if I take a weighted average of them, which is the arithmetical way of creating Simpson's estimate, then I'm going to get something that is a very good estimate. And you do find this once you get to Simpson's estimate and you have that ES is less than or equal to, instead of little k over there, we have capital K times b minus a divided by 180 times delta x to the 4th. That's the thing that really matters. Big K is just the largest possible value of the 4th derivative, which by itself is already nicer for most functions. As you take further derivatives, they sort of calm down a little bit. Not all of them, but very often. So this becomes k times b minus a to the fifth. To the fifth is a lot bigger, but in the denominator, 180n to the fourth. Now when I double the value of n, my error is cut by a factor of 16. This is a method that moves towards a good value very, very fast. Now, how do we use these? How do we take the error estimates and turn them into something where we can actually figure out useful values of n for any application? So let's say we wanted to estimate something straightforward. Let's take the integral from 1 to 4 of just x cubed dx. And we want to get this within 0.001, which means that we want our error estimate, our error bound, to be less than or equal to 0.001. And let's say that we want to do this using the midpoint estimate. So we have that the actual error is less than or equal to this value over here, k times b minus a, that's 4 minus 1, cubed over 24n squared. If this is less than or equal to 0.001, then we know that the error has to be less than or equal to 0.001. And so we set it up this way. So if we're setting it up, we tell people, let the error be less than or equal to this. And now we want to find out for what values of n is this going to be true. So our first step is going to be to figure out a value for k. Our function is f of x is equal to x cubed, which means that its derivative is 3x squared, which means that its second derivative is 6x. And I'm looking at 6x between 1 and 4. Right? In this case, I can find a precise value. I know that this is going to be biggest when x is equal to 4, and so I can just use 24 for my value of k. Right? If I don't have something this easy, I just overestimate. It doesn't matter. Right? It doesn't matter if I end up with a value of n that's higher by a few, or even by a factor of 2 or 3. For now, what we care about is figuring out how to get a good enough estimate. In later years, in a course on numerical methods, you may learn tricks that will help you figure out how to do it efficiently, how to find values of n which are as close to what you want as possible, as tight a bound as we can get. All right, but for us, this is more than sufficient. So we plug this into here, and so we've got 24 times 3 cubed over 24n squared is less than or equal to 1 over 1,000. Please use fractions where you can. There are going to be times where it's obvious that you want to just go with decimals and not worry about anything else. But if you can use fractions, you should. A little bit of simplification goes a long way. And so we end up with n squared is greater than or equal to 3 cubed is 27 times 1,000 is 27,000. And so n is greater than or equal to the square root of 27,000. Not ideal, but it'll do. At this point, if you can simplify it easily, you should. I might go as far as to take out a factor of 100, maybe even a factor of 900, and see what I get. Right? So if I take out 900, I would be left with 30 times the square root of 30. Certainly can't simplify it beyond that. But this is one case where you absolutely can just go to a calculator if you've got one handy, or if you don't, you leave it the way it is. If you want it to be a little bit more precise about things, we can't leave n as a decimal. N has to be an integer, as a matter of fact, a positive integer. So we can say it's the next decimal or the next integer beyond this, or you can use what is called the ceiling function. You will probably learn about this in some computer science course this year, next year. This is equal to the smallest integer, call it m, such that m is greater than or equal to x. So when I take the ceiling of 2.5, then this is equal to 3. When I take the ceiling of 4, then that's just equal to 4. So what we can do is we can let n be equal to the ceiling of the square root of 27,000, and that is certainly the kind of answer that we're looking for.